Good morning, good afternoon, and good evening to all of our attendees joining us today for this latest Data Science Central webinar. This is Bill Voorhees, your host. I'm the editorial director with Data Science Central and also chief data scientist for Data Magnum. I'd like to start off our event today by thanking TidalScale for sponsoring today's event. TidalScale has become an integral supporter of the Data Science Central community, and we're honored to have them sponsoring our event today. I'd also like to take this opportunity to mention and show our appreciation for some of our other recent sponsors, including HPE Vertica, Alteryx, Dell Statistica, IBM, Teradata, and Exaptive, to name just a few. Now, past webinars are available on demand at datasciencecentral.com, and if you haven't had an opportunity to view them, I encourage you to take a look. They provide some very useful insight into a wide variety of topics of interest to our data science community. Today's webinar is entitled, How to Keep Your R Code Simple While Tackling Big Data Sets. Now, before we begin, I'd like to briefly review the format of today's webinar. Today's event will be an hour long. We have one presenter that I'll introduce in just a minute. There'll be 10 or 15 minutes of Q&A following the presentation, and this event is being recorded and will be available on datasciencecentral.com later this afternoon following today's live event. Now, I'd also like to encourage our attendees to provide questions throughout the presentation, as we'll be reviewing and presenting them on your behalf during the Q&A portion of today's event. Now, I'm very pleased to introduce today's speaker, Michael Berman. Michael is VP of Engineering at TidalScale, where he focuses on developing TidalScale's ability to simplify the way companies can apply computing resources to big data problems. Now, previously, Michael was CTO at Catbird Networks, responsible for the design of Catbird vSecurity, the industry leader in security virtualization. Michael was also a principal at IS Data LLC, an elite enterprise security design and computer forensic investigation professional services company. And he performed hundreds of computer forensic investigations, designed enterprise security solutions, and led security assessments. So Michael served in numerous roles for his service customers: ISO 27001 Compliance Manager, Chief Security Officer, and Incident Response Manager. And prior to IS Data, he was Western Region VP of Professional Services for Predictive Systems, Inc., delivering security services and assessments nationally to numerous industries. Now, R, Tear, Spark, and Python are tools that all benefit from larger systems. Software-defined servers enable data scientists to size their processing systems to the size of a particular data problem. In this Data Science Central webinar, you'll learn how software-defined services work in practice for several common data science tools, and we'll explore how removing core and memory constraints has multiple profound and positive implications for application developers tackling big data problems of all kinds. So, Michael, with that, whenever you're ready, I'm going to turn it over to you. You can begin as soon as you want to go.
Thank you. Good morning, everybody. Thanks for joining this webcast. Bill gave me an excellent introduction. Again, thank you, Bill. You know, if you think about my career, my evolution to coming to TidalScale, I've always worked with data in the security side, and I continue to work with data at TidalScale, obviously. And what we're about is solving this problem of how to handle the velocity, the variety, and the constant changing data as it's coming in from retail stores, CCTV, now Internet of Things. And how do we handle that data, and how do we analyze it quickly for purposes of business intelligence, analytics, prediction, what have you. And what we know for sure is that getting it all into memory is vital. Looking at the right-hand part of this slide, you know, if we look at the different types of memory that's available, obviously the level 1 through 3 cache is the fastest, DRAM is next, NVMe flash, flash array hard drives, etc. We call that gap between DRAM and NVMe flash, we call that the memory cliff. Because once you're going to storage, even very fast storage, the amount of time it takes to load the data, analyze the problem, changes by orders of magnitude. That's the point of the dollar amounts on the right. Basically trying to relate that, when you're going up 2, 3 orders of magnitude, we kind of miss that change from nanoseconds to microseconds and then microseconds to milliseconds. So at TidalScale, we've called that the memory cliff. And what we're working to address and help data scientists address is get everything into memory so that your analysis is as fast as possible. So some of the current approaches that are out there today is to either subsample or use algorithms or to shard the data. And again, we're doing this because if we can't keep it all in memory, our ability to analyze and solve problems is reduced. It takes too long. And we can subsample, create a smaller data set to get it in memory, but that affects our prediction accuracy. Same thing with modifying algorithms. Or we can shard. And sharding, often impacts prediction accuracy as well. And there's the complication of that we have to rewrite the software, relay out the data. And as that velocity and variety keeps picking up, we're constantly having to shard and reshard again. But what if our servers were software defined? What if you could create a bigger server to meet the needs of your problem? Basically size the server to the size of your data set. Then you'd be performing in-memory performance at scale. You'd have all of that in-memory, in RAM, often in that cache, that high-speed cache as you're accessing it. You have all the cores you need. If it was self-optimizing and everything just worked, right, on standard hardware. So you don't have to change your programming model. You don't have to change programming languages. You didn't have to go from working on a single system to a distributed system. What would that mean to you? We're going to explore some of these concepts. So first, I want to explain how this works. What is TidalScale's approach technically? So in traditional virtualization, we have a single physical server and a hypervisor layer. That hypervisor might be ESX, KVM, Xen, Hyper-V. And the hypervisor creates these virtual machines on top of that physical server. And what's nice about a hypervisor is that you're then able to run the operating system, usually called the guest operating system, and it's completely unmodified nowadays. And so there's no changes to the operating system, there's no changes to the application. So the idea we had at TidalScale was to take this concept of traditional virtualization, but to, say, invert it. Sometimes I call this an inverse hypervisor. And so what we've done is we've created a hyperkernel, which is a kind of distributed hypervisor that runs on each of those physical servers. And then that hyperkernel stitches them together into a single virtual machine. So like a traditional hypervisor, you can then run an operating system and an application that's 100% bit for bit unmodified. No changes required. And that's the key element here, is that the languages or the tools you use for data science do not need to change to take advantage of this technology. And as your problem grows, as the volume goes up, as the data set you need to analyze continues to increase, you just add more servers, more individual worker nodes to that TidalScale cluster. We in fact decided to call it a tidal pod. If you go to our website at TidalScale, you see we have a very strong ocean theme, surfing theme playing throughout our website. And to play off of that, instead of calling it a cluster, we call it a tidal pod. So as you need a bigger software-defined server, you just add more physical nodes to your pod, and you get a bigger operating system, essentially more RAM, more cores for doing your data analysis. But that by itself, wouldn't be enough, right? Because you would still have this constant problem that people have with large-scale NUMA or super NUMA machines. And the problem I'm referring to there, and you can see this if you do work in clusters with Spark or other technologies, is that occasionally if you get it wrong and the worker thread doing the analysis and the data are not on the same nodes, you either get a failure, it doesn't work, or you just get a lot of latency on that particular query. But what we did at TidalScale is we analyzed the data. I didn't start out as a data scientist. I started out as a kernel engineer, got into security, started dealing with big data on the security side, and had to go through that same evolution of how do you analyze when you've got gigabytes or terabytes or petabytes of information. How do you do that? Well, at TidalScale, what we're doing is we're looking at that event stream coming from the operating system, coming from the application, and the machine learning layer in TidalScale is making decisions about where should the memory be. So actually, as the R or Python or any logic or database application is running, we're looking at the pattern of execution, and we actually move the memory around the cluster. All right, but we don't just stop there. We can also move the CPUs around. Remember, this is virtualization. So you actually have virtual processors, virtual I/O, virtual memory, and all of these things are mobilized in TidalScale, so they can move back and forth in the cluster, as I am showing you with this animation. And so that's happening dynamically in microseconds, and it's being driven by our machine learning. And that's what makes this work underneath the hood. That's what allows TidalScale to hide the complexity of a distributed computing problem from you, the data scientist. So you can focus on the data science, and our machine learning algorithm worries about the distribution of the workload. All right, and again, because this is a hypervisor, like any other hypervisor you're familiar with, everything just works. Whatever favorite operating system you have or software package you like to run will run on top of TidalScale. So again, I want to emphasize this. You don't need to learn a new language or a new operating system or new technologies. You don't need to translate your work to Spark or start using a database for R. You just continue using the applications that you're comfortable with. People may ask, what does this cost? Well, if you think of this as like a supercomputer, you're kind of right. But the advantage of TidalScale is that we're making use of sweet spot servers. So instead of having to go out and buy a 4P, a 4-socket or 8-socket or Cray computer, that's the red line in this graph, you're just buying, the current off-the-shelf commodity price server, with whatever makes the best economic sense in terms of RAM and cores per server node. You just add them to the cluster, what we call a tidal pod, and you get the amount of memory and cores you need for your problem. So you get what looks like a much more linear price performance curve when you're using TidalScale versus going out and buying a supercomputer. So what does that mean? Well, what it means is you get the cost effectiveness of scale out, but you're getting the software simplicity of scale up, right? If you were to take your problem and scale out with Hadoop or Mongo, well, you have to rewrite. You have to take what you've been doing in R or Python or some other tool set, and you need to convert it to Spark, or you need to convert it to a problem that can be solved by Mongo or Hadoop or one of these other scale-out solutions. With TidalScale, you get the scale-out economics, but you don't have to change your programming model. It's like a scale-up. It's like just having a bigger computer. All right, so what does this look like? Well, normally with scale up, you start running into a situation where it gets more and more expensive as the computers get bigger and bigger. But with TidalScale, you don't have that problem because basically we take those individual worker nodes as if they're, Lego building blocks. And if you need 5 nodes today, so be it. But if the next day you need more, you just, reboot with more. And you can keep going and keep growing and keep growing as your problem requires it. Similarly, we can simplify scale out. I mean, there may be some problems that don't fit in 20, 30, 40 terabyte systems like you can get with TidalScale. You might still want to get, a few hundred terabytes in memory, and you may still then need to run Spark across many TidalScale nodes. But the thing you get with TidalScale is you drive simplicity into the stack, because instead of having to run hundreds or thousands of nodes, you can run 5 or 10 or 20 TidalScale nodes. And that greatly simplifies the problem and the cost of having to maintain all those versions of all those instances of Linux, all those instances of your application, you can reduce that by a factor of 5, 10, or 20 trivially with TidalScale, which greatly reduces your operational cost. We have a prospect we're talking to, they have many, I'll say hundreds of thousands of systems in their data center. And just the idea of dividing the number of operating systems by 10 is very attractive to them. So again, that simplifies the data center problem in deploying these types of solutions at scale. There are many application use cases for this technology. Obviously today we're going to focus on data science, but just so you're aware of this, if it's not obvious, you can run simulations, retail analytics, business intelligence, bioinformatics, financial analytics, or data science on TidalScale. And obviously in this, today I'll be focusing on data science. All right, so as I introduce this talk, I was talking about the too much data problem, right? It's either coming in, it's coming in very fast, the velocity and variety are changing, the volume is climbing, I think I've seen numbers like 46% compound annual, so don't hold it against me if I'm wrong, that means we're doubling every 2 years at that rate. So it's really important to think about how we're going to continue to solve this problem over time, because now with the Internet of Things, I'm expecting that volume increase is only going to accelerate. And so we're going to need high productivity languages. We're going to need to perhaps constantly be adapting or tuning our algorithms. And if we also have to keep changing the algorithms we're using and dealing with other types of complexities like distributed computing grids, it just gets harder and harder to do this. And so it's important that the industry respond to this and allow data science to operate with the best packages, the best applications, the best languages to solve these problems. So for example, if we're trying to get more accuracy, right, one algorithm to use here is decision trees. And if we're looking for the right combination of error rate and observations, what we see is that this correlates to tree depth, right? So the deeper we can go on our decision tree with the larger number of observations, the more we reduce error rate, or the other way to say it is the more accurate our potential predictions become. So this learning time decreases with the tree depth, but we need more data and greater tree depth. That means more RAM, right? So if we want more accuracy and we want to handle more observations and we need to go greater tree depth, we need more and more RAM. And that growth in the RAM is not necessarily linear, right? Decision trees can be quadratic in space. So we're going to talk about that further. But again, with TidalScale, you can make an algorithmic decision. I'm going to use an algorithm that's memory hungry because I need a decision faster, or I need a better decision. All right, so let's just talk a little bit. It's always useful to have a couple of cautionary tales. So if we look at some recent events, first here, the Challenger disaster. There's a lot of different explanations about, what went wrong at NASA politically, perhaps what went wrong in the presentation of information at the time that they were making a decision to launch Challenger. But what isn't questioned anymore is if you have enough data, if they had really looked at and had the time to look at this, they would have seen that launches and tests in colder temperatures had a higher risk of failure, right, because of the damage to the O-rings that was being detected. And in fact, the Challenger launch, as you see to the far left, was, a terrible situation in terms of the temperature that day. So, but if you have the data, right, you're less likely to miss this relationship. So that's the key value here that I'm trying to present, that the more data you have and your ability to look at it in real time as the data is changing is vital. Another recent example is with the financial crash of 2008. So we packed a lot of information in this slide. So what you're looking at here is the frequency rate for mortgage default year to year from 2002 to 2007. And the prediction you would have made based on the model data, right, based on either 2002 through 2004, or if you were able to look at the data from 2002 through 2007. And here is where we see that a lot of people in the industry, their model did not include the most recent data. They didn't have the ability to fit it into systems and accurately model what was going on. And because of that, many people missed what was going to occur, right? But if you have the data, you're able to take in, that data stream as it's coming, keep putting it into memory and keep analyzing it, you're more likely to get a good prediction. All right, so here I'm going to go through an example use case. So we have a partner who's doing retail analytics on TidalScale, and they use the TPCH power test for performance comparisons. So this particular comparison is against the system in Amazon EC2, so commonly available instances there at Elastic Cloud. And as you increase the workload size at Amazon, you see this performance curve until eventually the system just stops responding. It's unable to handle the workload. But that same workload on TidalScale continues to run, and as you see in this graph, at near linear scale. And so basically what our partner is able to do is just add more servers to the Tidal pod and keep that workload in memory. And as such, keep the performance high, keep the response time, the latency to get a query answered low, and allow their retail customers to do this analytics of warehouse activity and customer activity to keep running that at scale. So in a similar vein, we've done a lot of work around the open source R packages, and we've created a benchmark which is available for download off of GitHub. You can find all of this information on the TidalScale website and pointers to the GitHub benchmark. And what we did is we worked with the CMS data sets. And we've gone through various sample sizes, testing that data set through these operations. So we've used in-memory footprints from 32 gigabytes to 680 gigabytes using standard 128 gig physical nodes. So obviously you can buy bigger nodes than that and use that in TidalScale, but the point was to do this comparison and show how by using these sort of cookie cutter, or I said Lego sized worker nodes, you can scale up the number of nodes, keep everything in memory. And so without that, you would have quickly gotten to the point where it was infeasible to analyze this data set. At some point, you exceed the amount of memory available in your server, and as many of you may know, when that happens with R, it may simply fail, but certainly the performance at best is fairly poor. But with TidalScale, you can keep it in memory, run all these operations, and in fact, at the 680 gig, which I believe is sample size 20 in the CMS data set, run all of these operations, load, join, GAM, GLM, decision tree, random forest. We use the fixed seed there so we can do reproducibility in terms of our benchmarking and performance analysis, and K nearest neighbors. And we can do the full 680 gig data set and do all of this analysis in less than 3 days. All right, so now let's look at some of the tools. These are just 3, there's many others, right? The point being that we enable you to continue using these tools, use other tools that you may prefer. Today I'm just going to go through these 3, Spark, Python, and open source R. Let's start with Spark. All right, so first of all, you would need to set up your cluster. Now on TidalScale, you would run Spark in what's called single node. or if you need a truly enormous Spark cluster, you do this with multiple TidalScale nodes. But if you were looking at this as an alternative, I could do this problem on Spark, or I could do this on TidalScale. These are some of the things you need to consider when you set up that cluster. And hopefully for those of you who are familiar with Spark, this will resonate. But you've got to look at your workload sizes. See this area over here on the green. Do you have the right number of JVMs? Do you have the JVM sizes correct? How many JVMs can you fit in a node? Do you get everything into RAM? You've got to work this all out. And sometimes it's not really clear how much memory you're going to need until you actually run the problem. And I'll be diving in just a moment into that in some detail. But what that means is you've got to feel your way through it. The first time you run this, it's probably not going to work. It's going to take 2 or 3 or more iterations. And you're going to be constantly having to modify what you're doing to work in this sort of distributed environment, because you got to keep chopping the problem up to fit the individual nodes you have available. But if you had one huge node or even a few very large nodes, it's easier to shard the problem and get it to fit. If you're familiar with the backpack problem in computer science, it's a lot easier to do first fit algorithms when you've got a big backpack. And so that's the same thing is true with TidalScale. It gives you a very big RAM footprint, makes it easier to fit the job into. All right, a few other things crop up with Spark. It's a distributed computing technology that runs on top of TCP/IP. You can have all sorts of issues crop up in the data center because of networking errors, because of latency changes. And it's not a very, it's not very robust yet. I mean, there's a lot of people working on it. I'm sure it's going to get better, but it's a young technology, is how I would put it. And we picked this up from that link below is where this slide comes from. This is an InfoWorld article on Spark, and I recommend looking at it. And if you are working with Spark, you understand these challenges. All right, so now let's look at Python. I expect many of you are experienced with Python. I happen to like it as a language personally. And, what's nice about this is you can, as a Python user, just run as you normally would on TidalScale. And no changes to the application, no changes to how you work. I will recommend that if you are doing a lot of work with Python and you're multi-threading, be aware of the global interpreter lock. It's a choke point in a multi-threaded Python application, and it's often necessary to sort of alter the structure of how you work with Python if you want to bring the number of threads up. Certainly, if you want to get to the hundreds, you need to program in such a way that you're not passing through the GIL all the time. But that's just an aside. That's a standard issue with Python. So this is some example code for running random forest. Similarly, if you want to go distributed in Python, something you would be able to avoid with TidalScale, but in Python you can do it, right? But you have some of the same issues you have with Spark. You have to figure out the distributed computing issues yourself. Set up that cluster, get everything configured, launch it all, get the data to where it needs to be. You now have to code to this parallel framework rather than, what I would call vanilla Python. You have to use the distributed frameworks, and you have to be constantly on top of it. And, constantly optimizing or re-optimizing if you have any situations where the data you need is not on the node where the Python, particular Python thread is executing that needs to analyze that data. So there's a lot of complexity with either using like the Hadoop file system underneath this, other technologies to get the data where it needs to go. Mainly that falls on either you or the IT people who are supporting you to do that sharding and laying out of data. And that's part of the problem in any kind of distributed computing technology that has to be addressed. Now let's look at R, right? I'm sure most of the people here listening are familiar with R, but there's sort of like the Achilles heel of R. It's got to be in memory. R was not designed to use swap or to page very gracefully. In R, all objects must be stored in memory. And so once you hit the ceiling of your laptop, your workstation, your cloud server, your data center server, it slows down to a crawl. And that's when many people have to go to one of these other technologies. You do your initial exploration, your initial kind of proof of concept in R, but then many people are faced with the problem, either downsampling or they have to rewrite and figure out how to shard it. And so let's go through that a little bit, right? What if you didn't have to do that, right? That's the point of this talk today. The technology we provide allows you to continue to scale the computer up to meet the needs of the problem. So this could be the entire CMS Medicare data set if you wanted it to be. The publicly available one is available to sample 20. You get the raw CSV data, you import it, and you can continue to do this analysis. And that's exactly what we did in our benchmark. And we used these models to do prediction around patient expense using age, gender, chronic conditions and drugs being used. And we went through GAM, GLM, nearest neighbor, random forest and decision trees, and to look at this and just to play with the data set. And with R, that's pretty darn easy. And with TidalScale, you just keep going, right? You don't need to rewrite. What worked on CMS 1 works on CMS 20. Now, I mentioned earlier, you need to be aware that there's a difference between, and many of you are, I'm sure, familiar with this, between how much space the data set may take up on disk and how much space that same data set may take up in memory. And so what we see here is that some of those factors, right? This is CMS 1. And, when you load it, it takes 6 gig. But when you go to join, the memory footprint more than doubles. It goes to 15 gig. And as we ran these different tool sets, the GAM, GLM, et cetera, the memory footprint continued to increase, as you see here, right, until that initial data set of 6 gig went to 18 gig. So in this case, it was about 3x the space on disk. And here you see that same view, right? If you look at this across the board going to CMS sample size 20, right, we've got the different sizes of the areas of the CMS data set. You've got the beneficiary summaries, the inpatient claims, outpatient carrier claims, the drug events, and those are the record totals for the 3 years. And those are those CMS sample, right? And what you see here is the actual in-memory size, right? Notice it says CentOS guest top there. So the point being that, that's what really, that's the memory requirements you really need to fit this all in memory. It's not the size of the CSV file. This is the resultant in-memory footprint as you ran, if you run this benchmark on these data sets. Now looking at, again, remember we were showing random forest, that's the comparison thread here, whether you're using Spark or Python or R, you can look at random forest here, and what we've got is really just, one of data science's favorite languages, very simple to use, clean, once you get used to it, and you're able to run a prediction. Now, what it turns out, unfortunately, as someone who's now middle-aged myself, is it turns out we become more expensive as we get older. Really no surprise there, but it's good to see that with the data and with these models, that they work, the data is good, the models are good. All right, so now let's say we want to compare the run times, right? We want to look at the specific tools we have here. As your memory footprint goes up, and you're using random forest, your execution time increases. But you don't fall off that memory cliff. Again, the more data you want to analyze, you just add some more server nodes to your cluster, your title pod, and you keep everything in memory. And so you continue to get, takes longer. Obviously, the data set is bigger, but rather than it being an exponential or parametric curve falling off the memory cliff, you just get this nice near linear scale. Now let's take a deeper look here. So if we look at open source R on TidalScale, we tested using Revolution R version 8, and again, that same public data set. And we went through the workload. Remember what I was showing you, that 128 gig server. So that goes off the memory cliff and it becomes infeasible to do this workload. And again, using TidalScale, right, we're able to run that same benchmark, no sharding, no code changes. You don't have to rewrite to a different language, no complexity in terms of distributed computing. From your point of view as a data scientist, you just use R, you just load the data in memory, and you do your job, right? And the end result is it's 240 to 550 times faster because it's in memory. And there shouldn't be a surprise there. If we go back to that first slide where I talked about the memory cliff, we're talking about orders of magnitude difference between RAM and any sort of stable storage like NVMe. So let's just wrap up a little bit on the tools here. So data scientists you have more tools than you've ever had before, right? But you also have more demands on your time and more complexity in terms of the volume and the variety of the data coming in. So this is basically a trade-off in your time, right? Do you continue to use the tools you're most comfortable with and in their own way are the most powerful for doing this data analysis? Or do you spend your time worrying about distributed computing and solving distributed computing problems? What I hope you're seeing here is that there's this technology at TidalScale that allows you to save that time, right? Continue using R, continue using Python, AnyLogic, whatever tools you like to use for your modeling and data analysis, and just keep using them without any changes. This not only saves you time in terms of programming and coding, but it allows you to do the analysis much more quickly because the data is in RAM. So we claim that this is a game changer, that a software scaled server, essentially a server that allows you to get the number of cores and the amount of memory you need for your problem. What I like to say is size the server to your problem, not vice versa, means that you can just do your job, get the work done, provide answers, provide more accurate answers using TidalScale than you can by downsampling or having to change algorithms or having to change languages or have to deal with the complexity of distributed computing. One example of this, we've run these tests as well at IBM, what was called IBM Software, it's now called IBM Bluemix. And there we set up a software-defined server with 15 terabytes of RAM and 400 cores. So at Bluemix, that was a complete rack of, in this case, 20 machines. And it just works, right? The same software, Red Hat, CentOS, Ubuntu, R, or Python, whatever you like to use, just works. And we have a nice little quote there from Mark Jones: software-defined servers make it easier to run memory-intensive applications like data mining, machine learning, and simulation. So that's sort of an example of what I'm talking about. If you need a 15 terabyte computer, the folks over at IBM will be happy to set you up at Bluemix. More information obviously can be had at our website as well. And I believe that brings me to my last slide. This is Gordon Bell founder, inventor of the VAX, the digital equipment. Also the first outside investor in TidalScale. And what he has said about us is that this is the way all servers will be built in the future. And with that, I'll wrap up and turn it back over to you, Bill.
Hey, Michael, thank you for that excellent presentation. Boy, that gives us a lot to think about in terms of our approach to speccing our server requirements. Well, let's get started with today's Q&A session. And I want to thank the audience for their participation. We've had a lot of questions that have come in during this presentation, and we'll do our best to get through them all in the time remaining. So during this Q&A session, I'll leave up this screen with contact information for Michael if you'd like to contact him following today's event. So let's get started. Michael, this really looks like a sea change in the way that we deal with storage and memory requirements. So how do you see the availability of the TidalScale solution changing the way that software developers approach problem solving?
Well, for example, in working with a couple of our application partners, what we've seen is people have been constrained by the size of the servers they have available to them. So just for example, if I'm working on my laptop, or I'm working on a server in the data center, let's say the server in the data center, it's got 128 gig of RAM. I know that when I run out of RAM, my performance is terrible. So if I'm using specific algorithms, I'll trade. There's a space for time trade-off, right? So I'll use algorithms that are memory thrifty or have a small memory footprint, right? Because I don't have enough memory, so I have to fit it. And I'll make decisions about the algorithm that maybe make it less accurate or slower, but it fits in memory. And if it didn't fit in memory, it would be terrible. But with TidalScale, I don't have to make that trade-off. I'll use an example in the bioinformatics case. There's two algorithms that we're aware of. One is SOAP de novo 2, and the other one is SPADES, S-P-A-D-E-S. And SOAP de novo 2 is one of these memory thrifty algorithms, and SPADES is one that's memory hungry. And if you've got TidalScale, go for memory hungry, because it's all going to fit in RAM, and because it all fits in RAM, it's more accurate and it's much faster. So it's kind of a little bit of a orientation, right? If you don't have a limit on cores, and if you don't have a limit on RAM, there's algorithms that may be better for your problem that until now were unavailable to you, or were infeasible because you didn't own a supercomputer, you couldn't afford it. And TidalScale is not quite a supercomputer. I'm not saying it's equivalent to one of the top 10 fastest computers in the world, but for typical needs in data science, a software scaled server is going to be 10 or 100 times faster than a traditional server. You just need to embrace this change. Go ahead.
No, I thank you for that answer. That's a real eye-opener on a different way to think about how to approach these problems. At the kind of at the bottom end of the scale, how do you advise your potential clients? How big does the data have to be to realize the sort of benefits that we're talking about here? Is there a rule of thumb threshold you can share with us?
Well, I think obviously I would say you're kind of better off starting with TidalScale. That way, as your volume or size of data grows, you don't have to make any changes. But obviously, if your data set fits in your laptop, you're fine. If your data set fits in, the typical server available to you in your data center, or the typical server available to you on Amazon, you may be fine as well. But the reality is that's just today. And the people we're talking to are basically faced with the problem that one company we've done some work with, their data set is growing at, something like 10% per month. It's ridiculous. And so even if it fits in a server today, it's not going to fit in a server for very long. So I would recommend get started with TidalScale. That way, you won't have to make any of these changes, a month or a few months down the road as your data set grows in size. Obviously, though, most of the people we're talking to are already dealing with multi-terabyte or larger data sets. And so they simply can't get the job done without using TidalScale. Most of the customers and prospects we have today, when they run on TidalScale, the first thing they say is, I've never been able to run this model before, or I've never been able to load my full data set before. 100% of the time, that's what they say. I've never done this analysis before. You know, they've always had a downsample. They've always had a compromise one way or the other.
Remarkable. Well, thank you for that answer. What about the other end of the scale? Are there any practical limits on the maximum size of a virtual machine, either by virtue of RAM and its addressability, or perhaps restrictions created by operating system limits to RAM or CPU or something like that?
Well, actually, there are. In the current Intel processor generation, with Linux, we're limited to 256 terabytes of RAM maximum today. That's with the Haswell or Broadwell chipsets, the V3 or V4 Intel. With Windows Server 2016, I think the limit is now 64 terabytes, but that, that's a software limit in Windows that would potentially go away and go to that same 256 terabytes, which is the current generation hardware limit. But in fact, Intel has announced plans either for the V5 or V6 generation, I forget which now, where the 256 terabyte limit will go away, and I believe it's going up to 16 petabytes, or petabytes if I'm correct. Don't hold me to that, but that limit will be going away in new Intel processor generation. So right now today with V3 or V4, the limit is 256 terabytes, but that limit will be going away.
Boy, it's hard to imagine being disappointed with 256 terabytes.
I know.
When we get to petabytes, that's that's almost mind-boggling. What is the largest TidalScale system that you configured to date? How big have you gone with this?
So far today, that was that system at Bluemix, the 15 terabyte system, but we don't see that as a technical limitation. That's just an operational limitation for us in terms of the hardware that was available to us at that time. Technically, there should be no issues with running TidalScale at much larger sizes.
Okay, thank you. Thank you for that answer. And is there a particular type of hardware that I need to think about if I want to run TidalScale? And does this need to be on-premise, or can it be cloud on demand?
Thank you for that question. So, well, our emphasis has always been on developing TidalScale for what I referred to in this slide deck as the sweet spot server. It's also, if you're familiar with the Open Compute project, we've taken great care to make sure that we are able to run on OCP compatible systems. So these can be Dell, these can be HP, these can be white box systems from Supermicro or Quanta. Any standard modern server will run TidalScale just fine. We don't have any requirements for special esoteric interconnects. We do require at least 10 gigabit networking for our magic. So we stitch together those servers using a 10 gigabit, either single 10 or multi-channel 10 gig if you desire. And that's what we use as our resource bus to stitch the computers in the TidalPod together. But other than that, 10 gigabit Ethernet networking, we don't require anything special. We don't require RDMA compatible controllers. We don't require any sort of esoteric InfiniBand or other types of networking to make this work. So probably the computers you have in your data center or the computers you have in your private cloud will run TidalScale just fine. Okay.
Well, thank you for that answer. You shared with me before the webinar that this kind of approach has been tried in the past and hasn't worked very well. What has TidalScale done differently to overcome these historical problems?
Well, I think there's probably many reasons why we are succeeding or have succeeded where people previously have failed. the two, let's see what comes to mind here on the spot. So one is the machine learning layer. So we took a hard look at locality theory. If you're familiar with Deming, who I'll call him the father of locality theory. He developed this idea when virtual memory was first being developed in the late, I'll say the late 70s. And the idea was that you could look at recent execution memory locality, and this was sufficiently predictive, not 100%, but gave you a good idea of where the next memory references would be used. And we now use locality theory in the silicon and chips for branch prediction. We use locality theory for content distribution networks on the internet. And TidalScale uses locality theory in the management of those virtual resources and the moving of memory and the moving of virtual processors around the cluster. So that machine learning layer and how it's continually optimizing for locality is very important. Another thing that's very important is that we allow you to run unmodified operating systems and not change. You don't have to run a special library. You don't have to change your application. That's another reason why we're being successful where others have failed. So other approaches to this, you did have to change your operating system. You had to run a special kernel. You don't need to do that with TidalScale. Another area where I think it's important is that we're all the 100% software solution. So going back to that question about specialized hardware, there is no specialized hardware. Prior entrance to this, people who tried to solve this problem before, for example, three-leaf systems had a solution for this. That required special hardware. Other folks out there, you can Google this, Super Numa, and I think it's NumaScale, that's special hardware. So again, because we're leveraging commodity hardware, we're keeping complexity down, reliability up, cost down. This approach is what allows you to succeed using TidalScale, where before you had to make compromises. There's I'm probably missing 2 or 3 other important reasons, but those are the top of mind ones.
Wow, that was very thorough, and thank you for that answer. In terms of going to market, do you present this as an add-on service like Amazon AWS, or is there an upfront fixed cost to be engaged with TidalScale?
And I'm sorry, and I may have forgotten to answer that. I think you asked something about cloud or on-premises. So
yes.
So sure. So TidalScale is a standard sort of cloud-ready subscription model. So you can get this from Bluemix, Orion VM, or other potential cloud partners that you may have or we may develop in the future. So you can get this, as needed, pay per use if you prefer. We also support standard software licensing model with on-premise deployment. And remind me, did I cover that? Did I answer that question? What was the other part?
Yes. Now I understand. Yes, thank you.
Okay.
Our audience obviously was paying attention that you talked a lot about R and Python, and they just wanted to confirm that their commercial analytic tools would also run in this model. For example, if you were running SAS or SPSS or KNIME or one of those other commercial packages for analytics.
Yes, absolutely. If it runs on, a Linux distribution today, it will run on TidalScale. There was a slide where I talked about Windows. We are running Windows internally. It just helps us have a better hyperkernel to run all the different operating systems we can. But we don't have general availability for, let's say, Windows 2016 yet. But that will occur in the future. But any package you're running on Linux will run on TidalScale and would be supported on TidalScale today.
Okay, good. Thanks for that clarification. Here's a question from an audience member that will give you an opportunity to perhaps cover some ground that you've already explained. But it's an interesting question because he asks, why wouldn't the hardware alternative work of, say, just plugging in 15 terabytes of RAM into a single machine not be just as good?
Sure. if you could do that, so there are technologies out there like NVDIMM, where you can plug in a lot of memory to that machine, maybe as much as 15 terabytes. I'm not sure if you can get quite there with NVDIMM yet today, but maybe you can. The problem, though, is you're not running on a standard operating system anymore if you're doing that. At least I don't think you are. And that may or may not cause you problems. It may require special libraries and changes as well. And no matter what, even though you're getting more memory, you're not getting more cores. And I want to go back to, one of the opportunities you have for running on TidalScale. Remember, I said you size the computer to your problem, and it's not just RAM, right? You can have more cores too. Remember the picture I had, the software slide, this one, right? This was not just, 15 terabytes of RAM, but it was also 400 cores. And you can get a lot of memory with NVDIMM. You can't get more cores that way. And that means that on TidalScale, you could be using an algorithm that's taking advantage of all those cores and the memory, and therefore getting your answers faster.
And Michael, I'm sorry to interrupt, but did you mean to take us back to this slide, or were you looking for one that was previous?
No, this one, the 15 terabyte and 400 cores. The point being that, you can put a lot of memory in the system with NVDIMM, but NVDIMM doesn't change your core count.
Got it completely. Well, thanks. And in terms of getting involved with TidalScale, is there a big learning curve? Is there a particular training requirement that's needed?
No, not at all. We've tried to make our software as easy to install as possible and as compatible with current DevOps state-of-the-art in terms of data center operations. And really, for the data scientist, there's nothing you have to learn. In fact, you could just keep using R. If you learned R in college and that's your preferred language and you never want to use anything else, that's fine. Just keep using R. If you like Python or SAS or SPSS, just keep using it. You don't need to change. It's just a big computer from your point of view. It's just, Linux with lots of RAM and lots of cores. You don't need to learn anything new. You may look at your algorithm and go, hey, I was trading space for time. I can now be memory hungry. Or I only had 30 cores. Now I have 300 cores. I'm going to change my algorithm to increase my parallelism. That you may want to do. But in terms of learning new languages or things of that nature, no, not necessary.
Well, Michael, thank you for some great answers to some very good questions. And for those of you that asked questions that weren't answered today, we'll be sending all the unanswered questions to Michael and TidalScale so they can follow up with you after today's webinar. Now, I have just a few quick announcements. If you would please mark your calendars for March 7th and our next DSC webinar, which is combining IBM SPSS statistics and R for competitive advantage, to be presented by IBM. Also, remember that today's taping will be available for on-demand viewing later today, and you can find that on the home page of Data Science Central in the Webinar tab located at the top of the page. Well, this brings today's webinar to a close, and I'd like to thank our audience for their attendance and thoughtful questions, and a special thanks again to TidalScale for their sponsorship, and our speaker today, Michael Berman, for his insight into today's topic. My name is Bill Voorhees. I'm very pleased to have been your host for today's event. I look forward to seeing you all again on March 7th. Have a great day.